Okie dokie. So, last week we made some cyclohexenes, hopefully. Maybe we've made some other unusual stuff. Sorry. And this week we're going to find out the identity. I mean, sometimes we won't be able to identify every single thing that we made, but a lot of them we will, and we're going to use GCMS, really mostly just the GC part of the GCMS, but I'll talk a little bit more about that here in just a second. So we'll be able to identify a lot of the things we made, and then we can also get an indication of what's the ratio, is this the major product, and very specifically, okay? And then we'll be able to take those ratios. You'll be able to take your mass. You came up with a mass at the end. Oh, okay, I made 130 milligrams of product material, okay? And you'll be able to take those ratios and go, okay, well, 10% of that was 1 methylcyclohexene, okay? And so you'll be able to get a percent yield for 1 methylcyclohexene based on the 10% of 130 milligrams. Does that make sense? Okay. There's a worksheet, and then at the bottom of the worksheet, there's like helpful hint document thing like that. I think that there's a lot in there, and it kind of answers everything you could possibly be concerned about doing this worksheet. But it's wordy, like me. I wrote it. So I apologize that it's not more concise. And what I always recommend, that you make key to life almost, is read everything 3 times. But for this one, definitely read the worksheet 3 times so you get what your goal is, what you're trying to do, and read that helpful hint thing just 3 times. Repetition, reps, right? Right, my athletes, reps. It's all about reps. Yeah. Okay. All right. Let's remind ourselves what the reactions that we did. Couple announcements. So you're going to take 10 microliters, incredibly small amount of your product, okay, and then you're going to prepare it and stuff for the GCMS upstairs. GCMS is extremely sensitive, so hardly takes anything. But I want you to, after you take out your 10 microliters, don't throw this guy away, okay? I'd like to save that in case somebody else spills theirs or something like that. So, make sense? Yeah. Was anybody, I know you weren't able to, but was anybody not able to get product last week? Sometimes we have, I didn't get nothing. No, everybody did, yeah? Woohoo! Kick a butt. Okay. Oh, yeah, that's why it's all blurry. There we go. The only way to get them to not fog up is do this librarian thing I got going on.
They have to sit on the tip of your nose.
What's that?
They have to sit.
Yeah, very tight. Luckily, it's pretty big, so I can really go out there. It's the first time I ever did that. Okay. All right. Expected versus unexpected. Product. Last week's the ones that I showed you were the products that we expected for those reactions. And you guys already have an appreciation that sometimes we get products that we don't expect, right? That's why when you did the eugenol and you looked at your TLC, there was maybe a little like streak down at the bottom and stuff. Those are unexpected products. Very common thing that happens in synthesis. Okay. So for 4-methylcyclohexanol first. remind ourselves what those are. I was going to say, and unexpected. This is really redundant. I don't know why. All right, so. One, there was only one quote-unquote expected product. H2SO4, H3PO4. And real quick, your part of the worksheet is writing mechanisms. You need to use CHEM sketch to write your mechanisms and stuff. So either it's on your laptop, you go to the computer lab, or you use VMware to get into the system. Okay. I just want to, again, I hate this part because I have to insult 99% of the students, and I just don't see any way around it. This has been one of the labs where temptation has overcome occasional students. Okay. So when you make your mechanism, that's your mechanism. You've got to make your own. You've got to do it. I know you're all using the same software. Doesn't mean your pictures look the same at all. It's just like if I draw a picture of a puppy, and Kara draws a picture of a puppy, there is zero chance that you could put our puppies on top of each other and it would be the same puppy picture. It's just, you're just using a computer to draw pictures rather than a pencil. Okay, all right. Yes. All right. Okay, so sulfuric acid, super strong acid, can protonate. Can you still see that? I think actually. I do it this way, but
is this the same mechanism from last week?
But I'm going to add to it.
Okay, great.
Okay, so you get that product. You can get this product, which as far as you know about elimination reactions now, that is inexplicable. And you can get this product. Also inexplicable. Okay. So now this guy can leave. We get our carbocation. It's a secondary carbocation. Oh, I didn't even talk about that. I will a little bit. Hydrogen. H2O. Grab that proton, electrons come in there. So we get that guy. Okay. You remember from elimination reactions, sort of to get the real basics of it, look at it and assess it, you look for a leaving group. This is going to become our leaving group, and adjacent protons. And then you can get a double bond between where the leaving group was and adjacent protons. So you can get a double bond there, you can get a double bond there. How in the world could you get one there? Okay? There's no leaving group attached to either of those carbons. That doesn't make any sense on the surface. Okay? All right, so how does that happen? Well, one reasonable way that would happen is alkenes actually can protonate themselves, especially in the presence of something like sulfuric acid. Okay, so this alkene can protonate, which essentially is reversing, right? It can reverse here. But any alkene can protonate at either carbon of the alkene. Okay? I almost like you can conceptualize it, even though it's not probably isn't realistic to what's happening on a molecular level, but you can conceptualize it like a gate. The electron pair is like a gate, okay? It can swing out this way, abandoning that carbon, creating the carbocation, giving you this guy. Swings out this way. Now my fingers are attached to the proton just like here, okay? But the gate can swing the other way. It can swing out that way. Proton in here, okay? And leave a carbocation there. Okay? So, I'll sort of draw my arrow from this carbon to sort of show it going like that. Now, you have a carbocation on that carbon. Now you can solve the problem. Adjacent protons, you got an adjacent proton here. If that gets deprotonated, you're right back there. But if that gets deprotonated, that's how you get that back. Make sense? Okay. All right. Now, how can we get this guy? The same kind of process. This alkene can protonate again. Okay. It can swing up like this, abandoning that carbon and leaving a carbocation. Or it can swing down like that, abandoning that carbon. Make some sense? Okay. What did I say last week about the substitution of alkenes in terms of stability? All alkenes are the same?
The more with increasing substitution, it was like more stable or
The
something?
more stable, yeah, exactly. And how substituted is this alkene? How substituted? Non-substituted? Non-substituted?
Tri-substitution?
What's that?
Tri-substitution?
Tri-substituted, yeah. Carbon thing, carbon thing, carbon thing, 1H. Tri-substituted. Di-substituted and di-substituted. Okay? I've now shown you that all of these alkene products can actually reverse, create a new carbocation, and start making the others. Okay? So they can all react again. All right? Which one of these do you think is least likely to react again? Left, middle, or right? Least likely to react. Why? Yes, you're right. I'm just looking for I'm just assuming that you pointing that way meant this way.
Yeah.
Good.
I would assume because it's the most stable.
It's the most stable. Exactly. Exactly. So these guys are kind of, carbocations, alkene, carbocations, alkene. You let this process go long enough, you're going to build up more of this because these guys are far more likely to start to go back doing this path. This one is less likely because more stable. Exactly. Good. Okay. That is sometimes referred to as the thermodynamic product. Okay? It's the more stable one. All right. Make sense? we suggested that maybe we get a little bit more. This guy, again, you can try substitute versus bisubstitute. Okay. A couple other products that sometimes we see. It will remain to be seen what you have in your mix. Is this guy. I gave you the names last time. This is 3-methylcyclohexene, 1-methylcyclohexene. And then this guy is methylidine. Spell that right? Methylidine cyclohexane. It's now ANE because there's no alkene actually inside the cyclohexane. Okay? The alkene is sort of outside. The methylidine describes that one. Okay. And then we get this wacky one. How, gosh, man. Okay. It's not even a 6-membered ring anymore. Right? This is a thylidine cyclopentane. How the heck do we get something like that? That must have undergone what we call a ring contraction. The ring went contracted from 6-membered to 5-membered. All right. Quick reminder of the mechanism here. Mechanism, I've described this as an elimination reaction. It can be a little bit more specific. It is an elimination reaction, and it is an E1 elimination reaction, but it's a subtype of E1 eliminations. It's called a dehydration, taking water away. And you'll notice we're losing water on this molecule, right? Okay. Sidebar. Carbocation stability. Okay. Just like carbons have substitution, alkenes have substitution, carbocations also have differing degrees of substitution. And actually, to figure out how substituted a carbocation is, it is the exact same way you do any carbon. Okay? You already know how to figure out if a carbon's primary, secondary, tertiary. Okay? You can do the same with carbocations. All right? And it turns out that the more substituted a carbocation is, the more stable it is, and by a lot. Okay? So that's primary carbocation. And I'm going to put these in order of increasing stability. Secondary carbocation, tertiary carbocation. Okay. Increasing stability. So much so that we actually say this is, that's a uniform. That basically doesn't exist. You don't ever get a primary carbocation. Okay? So really dramatic differences. And again, I'll let Dr. Morgan go into the reason why substitution helps stabilize a carbocation. Part of it is that the carbon-to-carbon bond, this carbon can say, sorry, I like to anthropomorphize. This carbon can say, oh my gosh, you got that carbocation. Let me lend you some electron density and help stabilize that. Okay? Hydrogens can't really do that. All right? But yeah, that's a bigger story. Okay, so, and tertiary carbocations are significantly more stable than secondary carbocations. Okay? If you have a secondary carbocation, that's a secondary carbocation, right? If there was no charge and I just asked you what type of carbon that is, you'd say that's a secondary carbon. It's bonded to a carbon. So that's a secondary carbocation. If you have a secondary carbocation that forms next to a tertiary center, a wacky thing can happen. Okay? And when organic chemistry teachers make tests, they love this. So this is a good one to, this is a little tricky thing. You know, when I make tests, I like to make tests 30% easy. 30%, yeah, totally, you know, no big deal if you studied it. 30% like, all right, let's separate the women from the girls and the boys from the men here. Okay? So this would be that latter type. All right. What can happen is you can get a hydride shift. When I say the word hydride shift, or hydride implies 2 electrons, okay? Proton is no electrons. Hydrogen is 1 electron. Hydride is 2 electrons. So what we get is a 1,2 hydride shift. What that means is this hydrogen is going to break off of that carbon and it's going to take both electrons with it. Okay? And it's just going to pop over there. And that'll no longer be a carbocation. Okay? Now why in God's name would it do that? Goes over there. Because he took both of those electrons, that carbon is now left with an incomplete octet, only has 6 electrons around it, and thus it becomes the carbocation. But what type of carbocation is that? Tertiary. That's a tertiary carbocation. That's what drives this process. It's what makes Mother Nature say, well, do this wacky move. Okay? Now, if you have that, H2O, come in here, electrons go down there. Oh, wait, nope, easy verb. I blew it. Does anybody want to tell me how do I get that? Now that I have that. What did I do wrong, Olivia? You're pointing your pencil again. I'm not picking it. Don't be mad, but you're doing this like you know the answer.
No, sorry, I was just doing it in the air.
What do you think? I think you're right.
I don't know.
Okay. I'll put you on the spot. I'm sorry. What else? Organic chemistry is always by analogy. So, analogously, how did I get this alkene to make that? Oh, I took an adjacent proton now, not hydride. I took an adjacent proton. That's not a good example because that's my hydride shift. How did I get this alkene here? I took an adjacent proton, it eliminated, and I got that alkene. So what do I got to do to get this guy from this? What's that? From where?
Take one of the neighboring proton electrons.
From where?
One.
No. What neighboring proton? Where's the proton? Tell me on the molecule. Where's the proton I got to take off? Can't just say neighboring proton. I just said that.
take it from sulfuric acid.
Top. There's 3 of them right there, right? That's the only way you can get that alkene. Just take that adjacent proton. That's the weird thing about skeletal. I can't remember if I told you guys. We teach you skeletal, you get it, like pretty quick. Okay, I got it. But you gotta get to the point where you're seeing those H's, even though they're not drawn here. There's an H up here. H2O. Oh, come on. H2O. Grabs that proton, those electrons pop down there, bam. Okay. Oh. Now, how in the world, this takes some doing. How in the world do you get to that thing? Okay? In order to show you how that could happen, and really, I can't think of any other way. I want to redraw this because I want that to just show my hydride shift, right? But you can have that particular carbocation, and he could decide to do something else. Okay. Rather than a hydride saying, "Oh, I'm going to break off and go bond with that carbocation." Okay. This carbon, that carbon there can say the same thing. Say, "Oh, you know what? That's an attractive looking carbocation. I'm breaking up with you and I'm connecting with that guy." Okay. So this carbon here is going to take both of these electrons and move over there. Okay? That's called a 1,2 alkyl shift. Because it's not a hydride anymore, it's an alkyl group. Okay. If that happens, you get something that looks, and I'm going to draw kind of funky so that you can still sort of see what it came from. Okay, now he broke off there and it's bonded there. Okay. If he broke off here, that means that that carbon right there now only has 3 bonds. Okay? It only has 3 bonds. That carbon there has a proton. Okay? Now, how do I get to that? From that?
Same thing we just did?
Yep. Take a neighboring proton, but from where?
The top.
That is a very good guess. Oh. But would give me that. That's not what I have.
Don't you take it from the middle, so that, the middle of the, not the top one?
Can my hand to go up or down?
Right there. I don't know.
Sure. There? Is that what you meant? Just say yes.
Yes.
Okay.
Just
There's a proton right there. You can always, when you're doing a mechanism, you can always look at the product to cheat, in a sense. Okay? That's where we gotta go. I need a double bond from that carbon. The only way that carbon is that carbon, the only way that can happen is if